Let me begin with something ordinary, because physics becomes most interesting when it hides inside ordinary things. You look at a phone screen, and it glows. That is all you notice at first. A rectangle of light, some moving images, a message, a face, a number, a small piece of daily life. But if you ask what is actually happening, the simple object in your hand becomes a whole laboratory. Electrons inside the screen are being pushed into different energy states. They fall back down. Photons are emitted. Those photons travel into your eye, strike molecules in your retina, disturb electrons there, and start a chain of electrical signals that your brain later calls seeing. You do not experience any of that machinery directly. You just say, I see the screen. But underneath that sentence is one of the strangest achievements in science. The theory that describes these processes is quantum field theory, and in its most famous form, quantum electrodynamics. It tells us how light and electrons interact. Now, when people hear the word theory, they sometimes imagine something vague, something unfinished, something halfway between a guess and an opinion. That is not what I mean. This theory gives numbers, sharp numbers, numbers you can take into a laboratory and check against nature. And when physicists calculated one tiny property of the electron, its magnetic moment, the answer matched experiment to about 12 decimal places. 12. That is not a casual success. That is the kind of precision that should make you stop talking for a moment to feel what that means. Imagine measuring a distance across a country and being wrong by less than the width of a hair. Or imagine building a clock so precise that its tiny drift becomes visible only after absurdly long stretches of time. The electron is not being measured with a ruler, of course, but the comparison gives you the scale of the achievement. Nature gives a number. Human beings, using equations scratched on boards and checked by machines and argued over for decades, get the same number, not roughly the same, not good enough, the same to a degree that feels almost unreasonable. Now here is where the story becomes uncomfortable. A theory with that kind of accuracy ought to feel finished. You would think its foundations must be clean, polished, settled. You would think mathematicians would look at it and say, yes, this is a perfect structure. Every step justified. Every object clearly defined, but that is not what happened. The practical machinery works beautifully, while the deepest foundation remains strangely difficult to pin down. One of the famous million-dollar problems in mathematics asks, in effect, whether a major part of this framework can be made fully rigorous in 4 dimensions. That is not a small technical complaint. That is the mathematical world asking whether one of physics' most successful engines has been properly built at all. I do not say this to make the theory sound weak. That would be too easy, and it would also be false. The theory is not weak. It is astonishingly strong where it can be tested. The strange thing is more subtle. It is powerful in practice before it is fully understood in principle. That kind of situation happens in science more often than people like to admit. You learn to calculate, you compare with experiment, the result works, then later, sometimes much later, you ask why the method had any right to work in the first place. There is a very human side to this. In real physics, people are not always walking around with complete certainty. They make approximations. They argue over signs and equations. They throw away infinities in carefully prescribed ways. They rename trouble when the trouble becomes useful. I have seen calculations where the first honest answer is infinity, which is nature's least helpful reply. And instead of giving up, physicists reorganize the question until something finite appears from the outside that can look suspicious. From the inside, it feels like repairing an engine while it is running, because the engine is too valuable to turn off. The uncomfortable fact is that this repaired engine keeps winning. It explains the behavior of atoms, the emission of light, the scattering of particles, the structure behind modern electronics, and the results of experiments so delicate that a careless vibration can ruin them. It has guided machines that smash matter apart and revealed patterns hidden far below ordinary perception. Yet behind its success there remains a quiet gap between calculation and ultimate understanding. So this is where we begin, not with a failed theory, but with a dangerously successful one. Quantum field theory does not invite simple confidence or simple doubt. It gives us answers of almost impossible precision, while leaving open questions that should have been settled long ago. That is what makes it worth examining. Not because it collapses under pressure, but because it does not. It keeps standing, keeps calculating, keeps matching the world, even while the foundation beneath it remains unfinished. For most of your life, the word matter probably brings up a simple picture. Tiny thing, little pieces, small solid bits hiding inside larger solid bits. If you could shrink yourself down far enough, you might expect to see atoms like balls, electrons circling like planets, particles moving through empty space, as if the universe were a box filled with invisible dust. It is a useful picture for school books. It is also deeply misleading. The trouble begins when you ask what an electron actually is, not how it behaves in a rough drawing, not how we label it in a diagram, but what it is in the theory that gives those impossibly accurate predictions. The answer is not a miniature bead. It is not a speck of hard substance. In quantum field theory, an electron is an excitation of the electron field. That sounds abstract, but the idea is simple enough. If you do not force it into the old picture, a field is something that has a value everywhere in space. Temperature across a room is a field. Wind across a valley is a field. The difference is that the electron field is not just a convenient map of something else. It is treated as the thing itself. So when you say, there is an electron here, the theory is saying something more precise. The electron field is disturbed here in a particular way. The particle is the disturbance. There is no extra little object riding inside it. A photon is a disturbance of the electromagnetic field. Quarks are disturbances in quark fields. The Higgs particle is a disturbance in the Higgs field. Space is not an empty container with particles sprinkled through it. It is filled with fields, layered through one another, present everywhere, even where no particle is being detected. This is one of those ideas that is easy to repeat and hard to believe. I know the old picture keeps coming back. You try to imagine a field, and almost immediately the mind sneaks a little ball into it. It wants something with edges, something you can point to, something that feels like a thing. But nature does not owe us that kind of picture. Sometimes the useful image is not the true one. Sometimes the familiar model is just a ladder you climb and then leave behind. A good example is sound. When you hear a note from a violin, you do not imagine a tiny object flying from the string into your ear. You understand that something is vibrating, and the note is a pattern carried through air. With quantum fields, the analogy is not perfect, but it helps. What we call particles are more like notes than pebbles. They are stable patterns of activity in something deeper. The universe is not a warehouse of microscopic objects. It is closer to a set of invisible instruments, each capable of producing its own kind of note. Now bring that back to you. Your hand, your face, your bones, your blood, the chair beneath you, the air entering your lungs, all of it is made from field excitations, arranged into persistent patterns. The solidity you feel is not the solidity of tiny rocks pressed together. It is the result of interactions, electrons resisting electrons, fields coupling to fields, forces organizing disturbances into atoms, atoms into molecules, molecules into tissue. What you call touch is not two solid things truly meeting. It is a negotiation between fields that does not make you less real. It makes reality stranger than the version we were first given. You are not an illusion. You are not a ghost. You are a physical pattern, stable enough to think. Speak. Remember and ask what you are made of. The word made simply changes meaning. It no longer means built from little permanent bricks. It means held together by relationships, interactions, and lawful motion. This shift matters because particles alone cannot handle the world we actually observe. In high-energy physics, particles can be created and destroyed. Light can become matter. Matter can turn into radiation. A fixed particle picture breaks down because it assumes the cast of characters is already decided. Fields solve that problem. The field remains. The number of particles can change. Excitations appear, disappear, combine, scatter, and transform while the underlying fields continue to exist. That is why quantum field theory begins with fields rather than particles. It is not because physicists wanted the story to be harder. It is because the simpler story stopped working. At small scales and high energies, nature does not behave like a collection of tiny marbles. It behaves like interacting fields whose disturbances sometimes look particle-like when measured. So when you look at matter now, do not imagine that the old picture has been slightly improved. It has been replaced. The table is still there. Your hand is still there. The screen is still glowing, but underneath the familiar surface, the world is not built from little things sitting in empty space. It is fields active everywhere, taking on forms that last long enough for you to give them names. If you accept, even reluctantly, that matter is not made of little solid pieces but of fields, then there is a consequence you cannot avoid. And it goes straight at another assumption that feels almost too basic to question, which is the idea of emptiness. We use the word nothing very casually as if it were the simplest state the universe can have, a place where everything has been removed, a clean absence, a perfect quiet. But once fields enter the picture, that quiet disappears. Not dramatically at first, but in a way that becomes impossible to ignore the longer you think about it. Try this with me. Imagine our books perfectly sealed. No leaks, no radiation getting in or out. Placed somewhere far from everything you can think of. Far from stars. Far from galaxies. Somewhere deep in intergalactic space, where there is no matter drifting through. In classical physics, this is easy. The box is empty. No particles, no energy, no activity. You could write the energy inside as zero and move on. That answer feels clean because it matches the picture we started with, where empty space is simply a stage waiting for something to happen. But fields do not behave like objects that can be kept out by walls. A wall can stop atoms, block light, reflect radiation, but it cannot remove the fields themselves, because fields are not things that enter space. They are part of what space is. Wherever there is space, the fields are already there. So inside that perfectly sealed box, the electron field is present, the electromagnetic field is present, the quark fields are present, all of them overlapping, all of them existing, whether or not any particles are being observed. At this point, you might still try to hold on to the idea that Feynman, the fields are there, but they are inactive, quiet, doing nothing. That would preserve some version of emptiness. This is where quantum mechanics refuses to cooperate. There is a principle that shows up everywhere in the theory, and it tells you that a system cannot sit perfectly still. If you try to pin down its energy exactly, something else becomes uncertain. If you try to force it into complete stillness, the description breaks down. The simplest way to see this is to think of a system at its lowest possible energy. In classical physics, that lowest state can be completely motionless. In quantum physics, even the lowest state carries a residual motion, a kind of unavoidable jitter. It is not caused by an external disturbance. It is built into the rules. Apply that to fields, and the conclusion follows, whether you like it or not. The fields inside your empty box cannot be perfectly still. They fluctuate, not wildly, not in a way you can easily see, but persistently, everywhere, at all time. The electromagnetic field trembles. The electron field trembles. Every field contributes its own tiny fluctuations. The box that was supposed to contain nothing is now filled with activity, subtle, continuous, and unavoidable. At first, it is tempting to treat this as a mathematical detail, something that lives in the equations but does not correspond to anything real. That was, in fact, a common reaction when these ideas were first explored. It is easier to believe that the vacuum is truly empty and that the extra terms in the theory are just artifacts of the calculation. But nature has a way of pushing back against that kind of comfort. When physicists looked for ways to test these fluctuations, they found one that did not depend on interpretation. Take two metal plates, place them extremely close together in a vacuum, and leave them uncharged. According to the classical picture, nothing should happen. There is no force between them, no medium to transmit pressure, no reason for motion. But when the calculation is done with quantum fields, something changes. The fluctuations of the electromagnetic field are not the same everywhere. Between the plates, only certain patterns can exist. Outside the plates, all patterns are allowed. That imbalance produces a tiny force pushing the plates together, not because something is pulling them, but because the empty space around them is not behaving uniformly. This effect has been measured, not once, not in a fragile experiment that might be dismissed, but repeatedly. With increasing precision, the force is small, but it is there, exactly where the theory says it should be. That means the fluctuations are not optional. They are not a convenient fiction. They leave fingerprints. They do work. So the idea of empty space changes. It is no longer a blank background. It is more like a restless medium. Even in its lowest energy state, if you had a detector sensitive enough, you would not see stillness. You would see brief appearances and disappearances of energy patterns flickering in and out, never settling completely. The word vacuum starts to lose its everyday meaning. It does not mean nothing. It means the lowest level of something that never quite goes to zero. And once you see it that way, the quiet of empty space is not really quiet anymore. It is simply subtle enough that most of the time you do not notice it. Once you accept that empty space is not quiet but filled with restless fields, the next step seems almost innocent. Like a bookkeeping exercise you could finish if you were patient enough. You ask a simple question. If all these fields are fluctuating everywhere, how much energy does that add up to? It sounds like the kind of thing a careful theory should tell you without much drama. You take each possible way a field can vibrate, assign it a small amount of energy, and then sum over all of them. That is all. No mystery. just addition. And then the trouble begins, not gradually, but immediately. There are not just a few ways a field can fluctuate. There are infinitely many. Long wavelengths, short wavelengths, patterns stretched across meters, patterns squeezed into scales, far smaller than anything you can probe. Each one contributes a little energy. If you add a few, the result looks reasonable. If you add more, the number grows. If you follow the instruction of the theory honestly and include every possible fluctuation down to arbitrarily small scales, the sum does not settle. It does not approach a large number. It runs away. It becomes infinite. At first, you might think this is a sign that something has gone wrong in the calculation. After all, infinity is not a physical measurement. You do not put a detector somewhere and read off infinite energy. But the difficulty is that the infinity does not appear only in some obscure corner of the theory. It shows up in places where you would expect ordinary, measurable quantities. Take the mass of the electron. You start with a basic value, then add corrections from the interaction of the electron with the fluctuating electromagnetic field around it. Each correction involves contributions from all those virtual fluctuations. Add them carefully. And again, the answer does not stay finite. The correction grows without bound. The predicted mass becomes infinite. The same thing happens with the charge. The same thing happens with other observable quantities. The pattern repeats often enough that you begin to suspect it is not an accident. It is a structural feature of the way the theory is built. If you follow its rules strictly, you get infinities where you expected numbers. Now, if you were approaching this from scratch, you might decide that the theory has failed. You might say that a framework producing infinities for basic physical properties cannot be right and should be abandoned. That would be a clean response. Logically consistent, and probably what most people would do in other fields, but that is not what happened here, because there was another fact that could not be ignored. Despite these infinities, when the theory was used carefully, it gave answers that matched experiments with extraordinary precision. So instead of throwing it away, physicists did something more subtle, and depending on how you look at it, more troubling. They found a way to reorganize the calculation. Instead of treating the initial mass and charge as the physical ones, they treated them as bare quantities, not directly observable, and allowed them to absorb the infinities coming from the fluctuations. The idea was that the infinities from the corrections could cancel against infinities hidden in these bare parameters. When you subtract one from the other, what remains is finite, and that remainder is identified with the measured value. If you say it slowly, it sounds almost like a trick. Infinity minus infinity equals a finite number. And yet, when done with the correct procedure, it works. You take the divergent pieces, you arrange them so they cancel. And the leftover matches experiment, not loosely, not approximately, to many decimal places. The method has a name, Renormalization. And it became the standard way to extract meaningful predictions from a theory that onitras produces nonsense. I remember the first time I saw this written down in detail. There was a moment where I expected the argument to resolve into something obviously rigorous, some hidden step that would justify the subtraction cleanly. Instead, what I found was a set of rules that had been tested over and over again because they worked, not because they were derived from an unquestionable foundation. You learn how to apply them, you check the results, you move forward. The discomfort never fully disappears, but it becomes part of the background. There is an important point here that often gets missed. Renormalization is not a single adjustment applied once and forgotten. It is built into the structure of the theory. Every time you calculate a higher order correction, new infinities appear. And each time you apply the same logic to absorb them, the consistency of the whole framework depends on the fact that this procedure can be repeated without introducing new, uncontrollable parameters. That is what makes the theory usable. If each new calculation required an entirely new set of arbitrary fixes, the whole thing would collapse under its own weight. So you end up in a peculiar situation. The raw equations produce infinities. The modified procedure produces finite, accurate predictions. The success of the predictions justifies the use of the procedure, even if the underlying justification remains incomplete. From a practical point of view, the theory is a triumph. From a conceptual point of view, it leaves an open question sitting in plain sight. If you step back, the pattern is hard to ignore. You have a framework that describes nature with remarkable precision, yet requires a careful handling of infinities at every turn. You have a method that works reliably, yet looks suspicious when you isolate it and examine it on its own, and you have a set of rules that everyone uses, even though explaining why they should be trusted is not as straightforward as you might expect. That tension does not stop the calculations. It does not prevent the theory from being applied, but it changes how you look at it. Instead of a perfectly finished structure, it starts to feel like something still under construction. Something that holds together well enough to be used, but not yet explained in the way you would have hoped. After everything we've just gone through, the infinities, the cancellations, the uneasy feeling that the method works better than it should, you might expect the story to drift into failure. Some clear breakdown where the theory finally contradicts reality and forces us to move on. That would be the clean ending. That would make sense? But instead, something far more confusing happens. The predictions keep getting better. Let me bring you back to that number I mentioned earlier, the electron's magnetic moment, because this is where the whole situation becomes almost impossible to ignore. The electron behaves like a tiny magnet. If you place it in a magnetic field, it twists, just like a compass needle aligning itself with the Earth. The strength of that twist is described by a number, and early calculations suggested it should be exactly 2 in certain natural units. That was a simple, elegant result. It looked complete. Then experiments improved, and the number wasn't exactly 2. It was slightly larger, not by much, just a tiny correction, but enough to matter. Now, here is where the theory earns its reputation. Instead of shrugging and accepting the discrepancy, physicists went back to the calculations, this time including the effects of all those fluctuations we talked about earlier. The virtual particles constantly appearing and disappearing around the electron. Each of those processes contributes a small correction, 1 virtual photon, then 2, then more complicated loops. You add them up, term by term, using the same renormalization procedure that seemed so questionable a moment ago, and the answer shifts from 2 to something slightly larger, exactly the way the experiment demands. Not only that, but as more terms are calculated and experiments become more precise, the 2 sides keep matching, tightening together like 2 gears that were somehow machined in complete isolation and yet fit perfectly. Today, the agreement extends to 12 decimal places. 12. You could spend an entire career calculating a single additional correction, and when it's done, it slides neatly into place, improving the match instead of breaking it. At some point, you stop thinking of this as a coincidence. You stop thinking of it as luck. There is clearly something deeply right about the structure of the theory, even if the way we handle it looks questionable when examined too closely. That tension between how the theory is used and how well it works becomes impossible to ignore. Now, If the story ended there, you might say we've learned to live with that tension. The theory works even if we don't love every step of it. And that's good enough for now. But physics has a habit of testing its own limits. And one of the most promising ways to do that appeared in the form of a heavier cousin of the electron, a particle called the muon. The muon is almost identical to the electron in its basic properties. Same charge, same spin, same interactions. The only major difference is its mass. It is about 200 times heavier. That difference turns out to matter a great deal because it makes the muon more sensitive to whatever else might be hiding in the vacuum. If there are unknown particles, unknown forces, anything beyond the current theory, the muon is more likely to feel their influence. Its magnetic moment becomes a kind of probe, a way of testing whether the theory we trust is missing something. For years, experiments suggested that it might be. Measurements of the muon's magnetic moment showed a small but persistent discrepancy with the theoretical prediction. Not a huge gap, not something obvious, but enough to raise eyebrows. Enough that people started to talk about new physics. You could feel the shift. Papers began to appear proposing new particles, new interactions, new extensions of the theory. The muon was not just another data point anymore. It was a possible doorway. I remember the mood during that period. It wasn't loud or dramatic, more like a quiet expectation building in the background. You don't celebrate too early in this field, but you notice when something refuses to go away, the discrepancy held on long enough that it began to look real. Then more data came in, better measurements, more careful analysis. At the same time, the theoretical calculations were refined, especially the parts involving the strong interaction, which are notoriously difficult to handle. Different approaches that had once disagreed started to converge. The gap began to shrink, not because one side gave up, but because both sides improved, and then, without any dramatic announcement, it was effectively gone. The experimental value and the updated theoretical prediction lined up within the expected uncertainty, not perfectly identical, but close enough that the difference no longer demanded an explanation beyond the existing framework. What had looked like a crack in the theory turned out to be a combination of incomplete calculations and limited data. There was no moment of celebration for that outcome, no sense of victory. If anything, it felt like something had been quietly taken away. The anomaly had carried the possibility of change, the suggestion that we might be forced to rethink the structure we've been using for decades. Instead, the structure held. So now we are left with something even harder to interpret. A theory that produces infinities, relies on carefully managed cancellations, and yet continues to predict measurable quantities with astonishing accuracy, even in places where we hoped it might fail. The muon did not break it. The electron continues to confirm it, and whatever is missing from our understanding, it is not revealing itself easily through the experiments we know how to perform. Up to this point, you might still hold on to a kind of cautious optimism, the idea that even if the theory looks strange in places, even if it relies on methods that feel improvised, it ultimately aligns with reality wherever we can test it, and perhaps the deeper issues will sort themselves out with time. But there is one calculation where that optimism does not survive contact with the numbers, and it begins in a place that now should feel familiar. The vacuum. We already agreed that empty space is not empty, that fields are always present and always fluctuating, even in their lowest energy state. Those fluctuations carry energy, not a lot individually, just tiny contributions from each possible mode of vibration. But as before, the trouble is not in any single contribution. It is in the sum. You take all possible wavelengths, all possible ways the fields can oscillate, and you add them up to get the total energy of empty space. This time, the result is not just inconvenient, it is catastrophic. If you perform the calculation in the most straightforward way, using the same logic that works so well elsewhere, the predicted energy of the vacuum is enormous. Not large in the sense of bigger than expected, but large in a way that defies comparison. A number so extreme that writing it down feels almost meaningless. And this is not just an abstract number sitting in an equation. In general relativity, energy has gravitational effects. It curves space-time. It influences how the universe expands. So if the vacuum really contains this much energy, it should have a dramatic effect on the structure of the universe itself. What kind of effect? The simplest answer is that the universe would not exist in any recognizable form. The expansion of space would be driven so violently by this energy that matter would never have had the chance to clump together. No atoms, no stars, no galaxy, no stable structures of any kind. Everything would be pulled apart faster than forces could bind it together. The universe would be a thin, rapidly expanding blur, if it could even be called a universe at all. But that is not what we see. Observations tell us that the expansion of the universe is accelerating, yes, but only slightly. The effect is real, measured through distant supernova and large-scale structure, and it is attributed to something we call dark energy, which behaves very much like a small, positive vacuum energy. The key word here is small. Compared to the theoretical prediction, it is unimaginably small. The difference between the predicted value and the observed one is about 1 part in 10 to the 122. That is not a rounding error. That is the largest known mismatch between theory and observation in all of physics. To make that more tangible, imagine predicting the weight of a single grain of sand and ending up with a number heavier than all the matter in the observable universe combined. That is the scale of the discrepancy. And yet, the same framework that gives this wildly incorrect result also produces some of the most precise predictions we have ever tested. This is what people call the vacuum catastrophe. And the name is not an exaggeration. It is not a small puzzle waiting to be refined. It is a sign that something fundamental is missing from the way we are putting the pieces together. The calculation itself is straightforward. The reasoning is consistent with everything we have used elsewhere, and still the answer is wrong by a factor so large that it cannot be dismissed as a minor oversight. Now, one way to respond to this is to say that some unknown mechanism must be canceling out almost all of that enormous vacuum energy, leaving behind only the tiny value we observe. But this leads to another problem, one that feels almost as unsettling. For the cancellation to work, it has to be unbelievably precise. Every large contribution must be balanced by another large contribution, arranged in such a way that nearly everything disappears, leaving only a small remainder. This is what physicists call fine-tuning, and it carries a certain suspicion with it, because it suggests that the numbers are not being determined by a clear principle, but rather by a delicate balance that we do not understand. You see the same pattern elsewhere. The mass of the Higgs boson, the particle associated with the field that gives other particles their mass, also appears to require a precise cancellation between large terms. The parameters that describe the fundamental forces often sit at values that seem unnaturally small or delicately balanced. Over and over again, the theory presents us with numbers that look as if they have been adjusted with extreme care, without telling us why. At some point, you begin to wonder whether this is a clue or a coincidence. Maybe there is a deeper structure, a hidden symmetry or principle that enforces these cancellations naturally, and we simply have not discovered it yet. Or maybe the situation is more complicated, And what we are seeing is the result of a selection effect where only certain values of these parameters allow complex structures, and therefore observers to exist at all. Neither explanation is entirely satisfying. One promises a deeper theory that has not yet been found. The other suggests that some aspects of the universe might not be determined by fundamental necessity, but by circumstance. Either way, the vacuum is no longer a quiet background. It becomes a central problem, a place where the theory that works so well elsewhere produces a result that cannot be reconciled with reality. And unlike the earlier issues, where careful methods and clever techniques allowed us to extract finite, accurate answers, there is no widely accepted trick here that resolves the discrepancy. The gap remains large and unexplained. So you are left with a picture that is difficult to ignore. The same framework that predicts the behavior of electrons with extraordinary precision also predicts a universe that should have torn itself apart before anything could form. The fact that we are here at all, able to ask the question, depends on that prediction being almost completely wrong. Now, the pattern is difficult to ignore. We have a theory that works with astonishing precision in the situations we can test, yet produces infinities when handled naively, relies on procedures that feel more practical than principled, and fails dramatically when asked certain global questions, like the energy of the vacuum. At this point, you might expect that the remaining task is simply to clean up the mathematics, to make the framework rigorous, to close the gap between calculation and foundation. That sounds reasonable. It is also where things become more complicated than expected. There is a result known quietly among specialists, but rarely emphasized in standard presentations, that challenges the way the theory is typically constructed. It shows that one of the central tools used in almost every calculation, the method that separates particles into free ones before and after an interaction, does not fit neatly into a fully consistent mathematical description of interacting fields. The details are technical, but the conclusion is simple enough to state. The picture we use to compute interactions is not, strictly speaking, justified at the deepest level, and yet it continues to produce correct answers. If that were the only issue, it might be treated as a technical inconvenience, but it is not alone. When you expand the theory into a series to calculate correction, the series does not converge in the usual sense. The first few terms behave well, and that is all we ever use in practice. But if you try to push the expansion to its logical limit, it does not settle into a final answer. It eventually breaks down. The method works because we stop before it fails. That is not a flaw you can ignore entirely. It is a sign that the structure we are using is incomplete. There are other hints of the same underlying tension. If you examine how the strength of interactions changes with energy, certain calculations suggest that at extremely high energies, the quantities we rely on would become ill-defined, growing without bound in a way that cannot be physical. In practice, this does not affect current experiments, because those energy scales are far beyond our reach, but it reinforces the same message. The theory we are using behaves like an approximation, not a final description. Faced with this, physicists have developed a way of thinking that changes the goal, rather than forcing an immediate resolution. Instead of insisting that the theory must be valid at all scales, they treat it as an effective description, something that works within a certain range of energies and distances, capturing the phenomena we can observe without claiming to be the ultimate layer of reality. In this view, the infinities are not physical disasters, but signals that we are pushing the theory beyond where it applies. The parameters we measure, mass, charges, coupling strengths, are not necessarily fundamental constants derived from first principles, but inputs that summarize the influence of deeper physics we have not yet uncovered. This shift is subtle but important. It allows the theory to remain useful without pretending it is complete. It explains why renormalization works. We are not removing real infinities from nature. We are adjusting our description to account for what we have chosen not to model explicitly. It also explains why so many quantities appear fine-tuned. If our theory is only part of a larger structure, then the values we observe may be inherited from that deeper layer, not determined within the framework we are currently using. But this perspective comes with a cost. It means that the theory does not answer all the questions it raises. It describes how things behave without necessarily explaining why they take the particular values we measure. It gives us a reliable way to calculate, but not a complete picture of what lies beneath. Naturally, this leads to the search for something deeper. A framework that would unify these pieces, remove the inconsistencies, and provide a more fundamental account of reality. Several approaches have been proposed. Some attempt to replace point-like particles with extended objects. Others try to quantize space-time itself. And still others explore entirely different mathematical structures. Each of these ideas has its own strengths and its own challenges, but none has yet produced a clear, testable prediction that would distinguish it decisively from the theory we already have. Meanwhile, experiments continue. Larger accelerators, more precise measurements, new observational technique. The hope has been that somewhere, some deviation from the current theory would appear, a clear signal that points beyond it. But so far, the expected signs have not materialized. The standard framework continues to match what we see, even in places where we might have hoped for failure. So the situation is not one of collapse, but of suspension. We have a theory that works extraordinarily well within its domain, a set of mathematical issues that suggest it is not complete, and a collection of proposed extensions that have yet to find experimental support. Progress continues, but not in the form of a clear transition from one theory to another. It is slower, more fragmented, moving through refinements and partial insights. There is something instructive in that. It reminds us that understanding does not always arrive as a clean replacement of one idea by a better one. Sometimes it involves living with a framework that is both successful and incomplete, using it where it works, questioning it where it does not, and gradually building the tools needed to go further. The fact that the current theory has not been replaced does not mean it is final. It means that whatever comes next has to account for everything it already does, right? While also resolving the tensions we have uncovered. For now, that next step remains out of reach. The theory stands, productive and reliable, but not fully understood, and the search for a deeper description continues without a clear map of where it will lead